get started. A couple reminders. We do a test next week. Test week from the day. Study guide is on LMS. Also, if you have missing homework, that's the last day to turn it in. Yeah. So. Okay. Today, we need to get into section 4 of chapter 12. And we're going to talk about phase changes. Phase changes. So basically, we are going to be changing what state of matter we're in. So we break it into two broad categories: phase changes that require energy, and then phase changes that release energy. Okay, so those are the two broad categories. And within both of those categories, we have 3 different phase changes. Okay. So we're going to go through 6 different phase changes as we talk today. 3 of them mean you have to put energy into whatever material you're talking about. And the other 3, you have to remove energy. So, okay. I will mention most substances can be in all 3 states. Some of them you have to get ridiculously hot in order to make them vapors. Others, you have to make them ridiculously cold to become solids. But most of them, at some point, you can create them, you can make them exist in all 3 states. Now, there are exceptions, but let's focus on the rules, not the exceptions. We are going to use water for our examples for the simple fact that water can exist as all 3 states in a relatively small temperature range, a temperature range that we are familiar with. If, for example, we wanted to talk about hydrogen, to get down to solid, we'd have to get all the way down to 13 degrees Kelvin, which is minus 260 Celsius. So that's really hard to visualize. So we're going to use water. So the first group that we're going to talk about are the ones that require energy. So we have to put energy from the environment into the material. Now I will mention, we haven't talked about thermodynamics, and we probably won't really get into them that much. But basically, energy can move, okay, in the form of heat from different substances. It will naturally move from areas that have higher energy to areas that have lower energy. It wants to even it out. Anyway, just with that knowledge, let's move forward. So the first one, we're saying that it requires energy. And the first change is melting. Now you're probably familiar with what melting is. Okay, you're going from a solid to a liquid. Now we have to put a little bit more energy in because, well, in a liquid, we have more motion of the molecules. Remember, this is kinetic energy, so we can take heat energy and change it into kinetic energy. So we get more motion, and so we go from a solid to a liquid. Pretty straightforward, right? Okay. You heat something up, you go from a solid to a liquid. You put energy into it. Now, that will happen for water at room temperature. Okay, there's enough energy in the room around you, unless you're in, a giant freezer or something, that the energy just moves into that frozen water, that ice, and it turns into liquid. How much energy is transferred, though? Well, it depends on what you're talking about. Okay. Different substances require a different amount of energy. It all depends on those intermolecular forces. Okay? Now, I am not going to expect you to do calculations with that energy. Just know that they exist, but we're not going to do that. So. But the temperature at which there's enough energy to change something from a solid to a liquid has a special name. It's incredibly complex. It's called the melting point. Okay. So what temperature does something melt? The melting point. Okay, makes sense. For water, melting point is 0 degrees Celsius. Okay. That's the nice thing about the Celsius scale, is that we defined it based off of water, and so it makes sense. Anyway, so the melting point is where there's enough energy from just the environment to change something from a solid to a liquid. Okay. So the next phase change, well, it would make sense that we've gone from solid to liquid. The next logical one is liquid to gas. Okay. We call this vaporization. Now, there's actually 2 different ways that we can have vaporization. Both of them, we're taking a liquid and changing it into gas, but we have different ways that this is happening. The first one is called evaporation. Evaporation. This is what happens. Let's say it rains and there's a puddle out on the street. Well, eventually that puddle disappears. What happened? It evaporated. It turned into a vapor. Now, evaporation happens at the surface. So if we have, let's just say we have a beaker here with some water. Evaporation is, well, there's a water molecule right here, and all of a sudden it gets enough energy to get kicked out. It has enough energy, and it gets just forced out. Evaporation is a fairly slow process, as it happens only at the surface. Obviously, as the temperature rises, this happens a little bit faster. Okay? If this water is 1 degree Celsius, it's not a whole lot of energy, not much more energy than what it would be if it was solid. But if this water is, let's say, 90 degrees Celsius, it's a lot more energy, and we're going to get a lot more evaporation. However, we can pretty much stop evaporation. If we close the container, then it's in. We put a lid on this. Okay? What happens is, eventually, we get so many water molecules that have turned into a vapor that no more can. Okay? It has to do with some physics that we don't need to get into right at the moment. But there's a specific amount of water, vapor, that can be held right there. And it creates a pressure pushing down on the water so that evaporation stops. Now I say stops, but really what happens is anytime one comes out, one is forced back in. Okay. Let's call that vapor pressure. Pressure definitely makes a difference. Okay. If we increase the pressure, it changes how things behave. And we're going to talk about that in a little bit more depth as we go. So that's evaporation. Surface level. Okay. It's a fairly slow process. Now the other type of vaporization is much faster. And what we are doing is we're raising the entire temperature of all of this to a point where even down at the bottom, okay, these water molecules have enough energy to turn into a gas, and they form bubbles, and they escape. If you spent time in the kitchen, you probably know what that's called. Boiling. So when you boil water in the kitchen, which you have to do for several things, noodles, rice, among them, okay, you are putting heat down here, okay, and get our fire. Okay. And we're putting heat into it. And what happens is those water molecules down at the bottom start moving faster and faster and faster until they turn into water vapor. And then we get those bubbles and they rise. Basically, what we are doing with boiling is we're creating enough energy to overcome any vapor pressure. Okay. So, once again, we have a specific temperature for these different things. Water, again, very nice. It boils at 100 degrees Celsius. Okay. But different things have different boiling points. For example, let's just say iron. Okay. Iron as an element, you get it up to 3,136 degrees Kelvin, so 3,136 Kelvin, which is approximately 2,800 Celsius. Iron will actually start to boil. That's quite a bit. That is the boiling point. Okay. So we've gone from solid to liquid and liquid to gas. But remember, there's one more phase change. What comes next?
Freezing point.
So freezing, that one is releasing energy. We have one more that requires energy to be put in. Sublimation. Sublimation is the process of going directly from a solid to a gas. Going directly from a solid to a gas. It is possible to skip that whole liquid thing completely. Just go straight from solid to gas. And we do call this process sublimation. It does happen with water. So next time it snows, okay? If you see a pile of snow, like that a snow plow has pushed, okay? Even if the temperature never gets above freezing, it will slowly get smaller and smaller and smaller. What's happening is that solid water is subliming to become water vapor. Okay. Another very well-known, I guess you would say, example is something called dry ice. You guys ever heard of dry ice? Yeah? Okay.
Is it made of CO2?
CO2, yes. So it's solid carbon dioxide. But what happens is, so it's really cold to get solid carbon dioxide. And you can use it where you want to keep something cold, but where liquid water would damage it. Because it goes straight from solid carbon dioxide to vapor. It goes straight from solid to gas. There are other examples where this happens, but we'll get into how you can tell whether or not that is going to happen later. Okay. So those are our three where we're taking energy and putting it into the material. Our other three are releasing energy. We're pulling energy out of that material. And the first one that the book talks about is freezing. And you're familiar with what freezing is. Okay, we take liquid, we pull energy out until it becomes a solid. Pretty straightforward. Okay. Once again, there is a specific temperature at which this happens. It tends to be pretty much exactly the same temperature as the melting point. Okay. You could see very, very minor differences, but really it's the same. Okay. Especially for this class, freezing point and melting point, we can consider the same temperature. It's just a matter of which direction are you going. Okay. The next one, condensation, to condense. And this is gas to liquid. Okay? We're pulling energy out, we're changing it from a gas into a liquid, condensation. You may notice this if you have a cold drink. Now here in Utah, the air is fairly dry, but I think you're both from areas that are a little bit closer to the ocean, where it's probably a little more humid. And so if you have something cold, it starts to form those little water droplets on it. Okay? And that is condensation. Okay? You're getting the water that is in the air. When it comes close to that cold drink, it is losing energy because the energy that it has is being put into the cold drink and it forms liquid. It's condensation. And then finally we have deposition, which, we've been doing opposites. So so far we have the liquid to solid opposite. We've got the liquid and gas opposite. Now we need the solid and gas opposite. So once again, it's possible to skip the liquid phase and go straight from gas to solid. Okay, and this is called deposition. One example of this would be frost on your windows of the car in the morning. If you leave the car outside, that is, if you're in a garage, then it's not typically cold enough. But we get frost, and maybe you'd see it on the grass in the morning if your car is in the garage. But there's water vapor in the air. It will come close enough to something that is cold enough and instantly become solid instead of liquid. Okay, so that's deposition. So those are our 6 phase changes. So we have the 3 that require energy. We've got the melting, we've got the vaporization, we have the sublimation. And then we've got the 3 that release energy. We have the freezing, the condensation, and the deposition. Okay. So. All right, let's talk phase diagrams. So phase diagrams, and there's a picture on page 429 of a phase diagram. Now, if you recall, I said that the pressure that something is experiencing can have an effect on this. And basically, what a phase diagram tells us, okay, on the x-axis, we have temperature. Obviously, temperature plays a role. Okay, so we put that on the x-axis. But on the y-axis, we put pressure because it also has a role. And so the phase diagram, we can say at this temperature and this pressure, what state of matter will we have? So we can look at this and say at 50 degrees Celsius and 1 atmospheric pressure, in this phase diagram for water, we find 50, we find 1, and that lands us square in the liquid phase. Now that makes sense. You should be able to already predict that, okay? At just normal air pressure and 50 degrees Celsius, you're going to find liquid water. Okay. However, at more extreme temperatures or pressures, you might have to look it up. Also, you might just not be familiar with that material. Okay. If I were to ask you, the pressures and temperatures related to, something like bromine. Okay, you probably don't know those off the top of your head, and that's okay. That's why we have the phase diagram. But anytime you cross a line in that phase diagram from one phase to another, that represents one of these phase changes. Okay. So if you're looking at the one on page 429, you've got that dotted line at 1 atmosphere. And as you follow it across, okay, at 1 atmosphere, it crosses that red line between solid and liquid right at 0 degrees. Okay, that's where the phase change happens. If you continue to follow it, okay, it crosses the blue line between liquid and vapor at 100 degrees. That's the phase change. Now notice, if we increase the pressure, those lines are going to be in a different spot. If we decrease the pressure, those lines are going to be in a different spot. Okay. So it makes a difference. I'll point out a couple things on here. What you're going to see is at lowest temperatures and highest pressures, it's going to be solids. Okay. In the middle, you're going to see liquids, and at highest temperatures and lowest pressures, you're going to have vapors. There's a couple of other things, okay? I'll mention the critical point, which in this diagram is labeled B. It's on the upper right-hand side of that phase diagram. As it says in the book, this point indicates the critical pressure and critical temperature above which water cannot exist as a liquid. Okay. So if you have, basically once you get to that, if you start putting more and more energy in, it's just not going to turn into a liquid. Okay. Once you get to that temperature and pressure, start putting more energy in, not going to work. Okay. And then in the lower left, we have something that's marked the triple point. Now the triple point is actually really interesting. It's basically where all three phases come together. And so at that temperature and pressure, you have all three phases at the same time. And just because it's really weird, I'm going to bring up a video with the triple point of water. And we literally see ice boiling and freezing at the same time. So you can hear the air pump going, they're changing the pressure. So it's kind of all gone solid there, and then it just boiled. So here it's boiling while it's freezing. So that's what happens at the triple point. You get all of those different things happening. So, being able to read a phase diagram, I'm pretty sure that on the study guide it says you need to be able to read them. Of course, each element is going to be unique, or each substance, I guess I would say, because they're not all elements. I will mention sometimes they can have an unusual phase on there. If you look on page 430, that phase diagram for carbon, it actually has a fourth phase. And it's diamond. Okay? So we talked about how carbon can form this covalent network solid, being a diamond. Okay? And so here on page 430, we see that at these intense pressures, carbon changes from being graphite to being diamond. Now, graphite is still solid, but under the right conditions, it will change from being graphite to diamond. That is an interesting thing because at that point, it can move into one of the other areas, and it doesn't necessarily change it, if that makes sense. You can take a diamond and reduce the pressure and put it in a vacuum, and it's not necessarily going to become a vapor. Although it does also say that to become a vapor, you have to make it really, really hot as well. So I'm not saying that diamonds are completely indestructible, but if you were to take that diamond and move it back into the graphite range, it would remain a diamond. So. Okay. And that is the end of chapter 12. Any questions about what we've talked about today? Okay. Well, I have one last homework assignment for the semester, so I will let you get started on that. You should have plenty of time to work that. Once again, this is in the end of the chapter, and it's pretty straightforward. 75 to 82. So. All right, we can get started.